Okay, welcome to lecture 18 of CSE 548, the analysis of algorithms. Let's start off. First of all, are there any questions about logistics or course material? Start things off. Okay, one thing that we question.
Can you solve problem 16.2?
Can I solve problem 16.2, or can I talk about problem 16.2? It's probably a better question. Does anybody have a textbook here? Okay, one problem that a lot of people have been having on the homeworks, okay, let's try this and see if we can make this work, is problem 16.2, which was a dynamic programming problem. Okay, and let's just take a look quickly. Problem 16.2 is what you wanted, right? So I think what we wanted to discuss was this one. Let's zoom in here. Okay, the problem of printing neatly, because a lot of people have been having problems with it. Let's read the problem and see what the issue is. Consider the problem of printing a paragraph on a printer. The input text is a sequence of n words, each of which has a given length. Okay? You want to print the paragraph neatly on a number of lines that holds a maximum of m characters each. Okay? Our criteria of neatness is as follows. Given a line that contains a certain set of words, okay, we leave exactly one space per word. The number of extra spaces at the line is this. Does this make sense? You've got a certain number of total characters. You subtract the amount of space that you need for each word, okay, plus that j minus I tells you how many words you've got, and you've got to have a space between them. J plus I, okay. Or well, actually, it's I minus j. But the point is that this is going to be total space, the length of the words, and the gaps between the words. Everything else will be left as blank space at the end of a line. Okay? The goal is to minimize the sum over all lines but the last of the cubes of the number of extra space characters. Now this seems confusing. Why are we messing around with cubes? Okay, let's think back to what the problem is. The problem is we've got a set of words that we'd like to represent. We've got a paper. The paper is the thickness of the paper. Okay, the length of the paper is m. That's how many characters per line we can fit in. And we're building a text formatter. We're going to be putting words, trying to decide which line each word should go on. Let's say, like, here's a set of words. You can see the big words take up more space than the little words. Okay? This is one way to lay out this paragraph. Okay? Is this pretty or ugly? Okay? I think it's ugly because you've got this big gap here. Wouldn't it be nicer if, let's say, we had put on this, well, let's think about what we could have done. What we could have done, perhaps, was put this word further down. Another way we might have been able to do this, again, my drawing's imprecise enough, I have my freedom. But one thing we might have been able to do instead was to put this thing down here, the first and second word, move the next words down, then put these two words down. Okay, now we've counted for all of these words, and now continue as we did before. So you see that there's different flexibility. You've got some choice as to what you can put on what line. We're trying to come up with the prettiest layout. How do we measure prettiness? Well, in general, there's no real problem leaving a little bit of extra space at each line. The place where things get really ugly is if in the middle of a paragraph you've suddenly got this huge gap. Correct? And so a reasonable criteria to minimize ugliness would be try to avoid large gaps, large blank spaces at the end of lines. Maybe you're willing to have, for the purposes of making it pretty, a few more total spaces at the end of lines in order to minimize the problems of big clumps. Okay? How many people accept that that's a reasonable thing to want to do? Okay, most people. How many people don't accept that? Okay? So how do we get the effect of telling the side, of scoring, that this is better, that this is uglier than that? Well, one thing we can do is, instead of just summing up the space that's left at each character, let's say that there's one free character there, one free character here, 10 free characters here, 2 characters here. Let's say in this lineup they were, let's say, 3 free characters at the end, 4, 4, 4. Okay? The total of this is going to be what? 15. The total here is going to be 14. The total amount of wasted characters here looks worse than there. So if we just try to minimize the total number of blank spaces we save, there's no penalty for a big ugly thing. But what happens if instead we sum up the cubes of these things? What's this going to be cubed? 27, right? 64, 64, 64. That comes out to be what, about 200? Roughly 200. What happens if we cube this thing? It's 1 plus 1 plus 1,000 plus 8. This big ugly thing scores a lot worse when we cube it. This is the whole idea of asymptotic growth. You have a cube is a function that grows faster than linear. So if we sum up a bunch of the cubes of things, big things have a much harsher penalty than before. So our goal in this problem is to find a layout that minimizes the sum of the squares. So this layout, the sum of the cubes of the remaining gaps. So this layout would become better than this layout. Okay? Any questions about that? Question?
Why cubes, not squares?
Why cubes are not squares? Because they say so. Algorithmically, it's not any different if you try squares. Okay? I guess studies have shown, presumably, that cubes look better. Okay? But that's now an aesthetic criteria. Whatever aesthetic criteria you pick, you should be able to use dynamic programming to find the right one. Yeah?
You could consider like negative spaces. Then probably cubes make more sense than squares.
So you're saying if you have negative space, so you're saying that because, let's say, if you have a negative space, you mean that you overflow the line. Is that what you mean?
Yeah.
If you overflow the line, now you have a penalty of negative. Well, when you sum the cubes up, that would not hurt you to have a negative. Presumably you'd want this. This is an ugly thing too. So maybe you'd want to take the absolute values if you overflow it or something like that. But here you're not allowed to overflow it. Okay? Cubes instead of squares, just that's the way they chose it. But it should be clear that there's many different solutions. There's an optimal solution. Are you allowed to rearrange the words in the text? No, that would be a very creative text formatter. Okay? So you have strings that can't be rearranged. This should smell like dynamic programming. Okay? You're sticking in separators. One way to think about it is each blank line is a separator. Each carriage return, you tell where do you hit the next return. Okay, that's sort of like where do you put in the multiplication signs in your multiplying matrices. Okay? Now that you've got an optimization function problem, try to coming up with a recurrence for this. Figure out what would you like to know about the first n-1 words to help you figure out to give you the answer for the solution for n words. That's the idea of formulating a recurrence. You want f sub n. What will they have to tell you about different solutions for the first n-1 words to make that easy? Okay? And that's now where you're now thinking recursively, thinking like a dynamic program. Any questions? Okay? Think about it, and I hope. Okay, and it's not an easy problem. At least now you understand where it comes from. Okay, any questions? Here, let's take that back. Okay. Other logistical things. The midterm is not tomorrow, but it's going to be the Thursday after break. We'll cover everything up to graph algorithms. The programs will hopefully come back next class along with the results of the contest. We've had some problems running things because of different portability problems, and we wanted to also make sure everybody turned in their assignment before we gave them back. So that's what the delays are. Okay, any questions? Okay, what I'd like to now talk about, last class we talked about applications of depth-first search to a lot of different graph problems. We spoke about doing topological sorting. Okay, and that was a useful thing, and the algorithm isn't that complicated. We spoke about connected components, strongly connected components. And that should be clearly as a useful thing. Okay, maybe that algorithm is a little bit more complicated. Okay? What I'd like to talk about now is another application, another important graph problem, okay, that comes up in a lot of applications, finding minimum spanning trees. Okay, and the flavor of this is going to be different than the depth-first search algorithms. Some of the depth-first search algorithms, the details are quite tricky. Okay, and I don't expect people to necessarily understand the real details of some of the things, like the last algorithm we talked about for strongly connected components. But it is important to understand what the problems are and why they exist. Okay, why you might want to know about them. Okay, and for some of the simpler problems like minimum spanning trees, it's important to understand these algorithms because there's some useful lessons that come out of it. So what is a minimum spanning tree? A tree in a graph, okay, is a connected graph with no cycles. That should be, we've used that word tree lots of times, that should be clear. A spanning tree, okay, of a graph is a subgraph of the graph which has the exact same set of vertices and is a tree. Okay? So let's just play a game here. Suppose, let's say that we have our graph looks like this. Our graph is a cycle on, let's say, 6 vertices. How many different spanning trees are there of this graph? And if it's a cycle on n vertices, it's n spanning trees. Why? Because you delete each one of these edges. No matter which edge you delete, you get left with a tree. And there's no way you can delete 2 edges and end up with a tree. Okay? So this graph has n different spanning trees. How many edges does this how many spanning trees does this graph have? 1, it's just itself. Okay? How many edges does the complete graph on n vertices have? This is not obvious. This you have to have been told. Okay? But does anybody have any ideas how many spanning trees a graph on n vertices has, a complete graph? Turns out to be n to the n minus 2. Okay? So an exponential number. So there are a lot of different, a graph can have a lot of different spanning trees. Okay? May have a few or it may have a lot. Okay? We say that a spanning tree is a minimum spanning tree of a weighted graph, okay, if it is the tree whose sum of the edge weights is minimized. So what are we now talking about? This, unlike any of the problems we've talked about so far, I believe, is a problem on weighted graphs. Every edge will have some kind of a weight associated. Perhaps, let's say, the distance. If this map represents the, a road network, it might represent the distance between 2 points. Or perhaps if this was a friendship graph, the weight between 2 friends might be how well do they know each other, how good friends are they. Okay, maybe you don't want any wishy-washy friends. Okay? So if we have an edge-weighted spanning tree, an edge-weighted graph, a minimum spanning tree is the spanning tree whose edges sum to minimum weight. Okay? So there are potentially n to the n minus 2 different spanning trees. One way you could find the minimum spanning tree is to construct every single one of them and add up the edges that are in that spanning tree. Okay? And find the one that minimizes that sum. But that clearly is an expensive algorithm. Okay? In general, we need to be able to find minimum spanning trees in a much faster way. Okay? And in fact, there are several good ways to do that, and that's what I'd like to talk about. Okay? So what can we say? We should be able to agree that there can be more than one minimum spanning tree in a graph. Suppose we took this graph and every edge had the same number, edge weight. How many different minimum spanning trees does that graph have? N, because we could delete any edge. Suppose each edge had a different weight. 1, 2, 3, 4, 5, 6, 7. Okay? What would be the minimum spanning tree of this graph? Delete. The minimum spanning tree is the edge of minimum weight. Okay? So we would delete the edge 7. Okay? Algorithmically, it turns out there's not really any difference between a minimum spanning tree and a maximum spanning tree. Because if you make all these numbers negative, the minimum spanning tree, what would be the minimum spanning tree of this graph? Drop the smallest, this edge, correct? Because if we delete this, we're now deleting the smallest, the largest number. Okay? And if we didn't have the negative signs, that would be a maximum spanning tree. So the bottom line is, and this I didn't mean to be too confusing, minimum and maximum spanning trees are really equivalent problems. Okay? But the bottom line is that the problem itself has a long history. Okay? And the history keeps getting longer and longer. Okay? Because people keep finding, the more they look at old math journals, they keep finding older and older papers where somebody actually sat down and computed minimum spanning trees. Originally, computer scientists came up with the problem in the 50s. Okay? And the two algorithms we'll talk about in this class date back to the 1950s. But as people started reading it, there was an algorithm going back in a Czech journal in 1926. And recently, I've heard rumors of a paper from like 1905 that did about the same thing in some other, a relatively obscure place. Okay? But minimum spanning trees turn out to be very important for 3 reasons. Okay? There's always taught in any algorithms class, the one thing I can guarantee you is they'll talk about minimum spanning trees. Why is that? Well, first of all, it arises in a lot of applications. Okay? And so you have to be aware of minimum spanning trees in order to correctly solve a lot of problems. Okay? And I'll go through the applications a little bit. Second, as an algorithmic example, okay, minimum spanning trees will prove to be important in the sense that the greedy algorithm happens to always give you the optimal answer in finding a minimum spanning tree. What do we mean by the greedy algorithm? The greedy algorithm is usually what you would think of as somehow the obvious algorithm. What would be an example of a greedy thing to do in finding a minimum spanning tree? Right, so what would be the obvious thing to want to do when you're given a graph to find the smallest set of edges? You would say, well, pick the smallest edge. Start that and put that in the tree. And then pick the smallest remaining edge that can't hurt me. And the smallest remaining edge. Okay? That's a greedy thing. It's sort of gimme, gimme, gimme. Okay? The greedy things, usually greedy algorithms do not give you the right answer. Okay? For example, if we think back just a moment ago to that example on paragraphing. Okay? I'm putting words into paragraphs. If you stuff each line as full as possible, okay, given each word, stick it on the last line that's possible, that is not going to minimize the sum of the cubes. That might get you into a bad situation where you create a big gap. The amazing thing is about the minimum spanning tree problem is, in fact, that greedy algorithm always will work, give you the right answer. Okay, and we're going to prove that. And it's important to be able to see that sometimes you can prove such things. Okay, and it's a question of the structure of the problems. Okay? Any questions about greedy algorithms, what I mean? Finally, the other thing is that kind of neat about minimum spanning trees is that although the basic idea is the greedy algorithm, in order to really make them run fast, you need to use somewhat clever data structures. Okay? And it sort of illustrates the paradigm of you start out with an idea. The idea is basically the greedy algorithm. And then you hit it with a clever data structure to solve what's the bottleneck in that. Okay? And that's sort of an important lesson from algorithm design. Okay? Any questions? Okay, why would someone care spanning trees? Okay? Turns out there's several reasons why minimum spanning trees are useful. Okay? A lot of the original work on minimum spanning trees came as a result of the phone company. Okay? What was a problem that the phone company had? You've got a bunch of houses. sitting out in Nebraska or whatnot, okay, wherever houses sit, okay. Wire. Why? Because all these phones have to be connected to each other, or else obviously this is pre-cellular, okay. You have phones that had to be wired together. How do you go and connect them? Well, what's the criteria that you want? Clearly, all the phones have to be connected. What do you want to do if you're the phone company? What is your goal to minimize? Use as little wire as possible, because each wire is not so much necessarily the cost of the wire, but you got to build the trench, you got to put up the posts. What you try to figure out is how can you connect these things in a way as to use the minimum amount of wire. Okay, I'll make a guess that that's actually it. Okay? So in this case, it should be clear that the minimum spanning tree problem comes up is exactly what you want. Okay? Find a way to connect the set of points using the smallest amount of wire. Okay, that's exactly what minimum spanning tree is. Okay? And what's the weight in this? That's a good point. The vertices are going to be the houses. The weight is going to be the distance between the houses, or maybe a little bit different. It's actually more general. It could be more general than just the distances. Suppose, let's say, that between these two houses, there happened to be a mighty river, okay? And you didn't want, it would be, you could build a suspension bridge across this river to connect those. The correct model of that would not be the distance, but the cost of building the bridge. So a more general formulation would be not to just have it be the distance between them, but the cost of connecting them. Okay? And there's going to be nothing that isn't going to make any difference to our minimum spanning tree algorithm. It works no matter what your distance edge weights are. Okay? So that's the general formulation. Okay? Another case where the minimum spanning, yeah, question?
The underlying graph would be a complete graph.
Okay, so the other thing is that, that if you use the formulation now, okay, well, it depends what you mean, okay? Suppose, let's say that if you want to think about modeling, let's say, the phone network problem, okay? One way you could do it is model between every pair of locations. You could figure out what the cost is and make that a complete graph. Sometimes it may be the case that certain edges are so obviously prohibited that you don't bother to put them in there. You could represent them at a cost of infinity, let's say, and make it a complete graph. But sometimes, let's say, you're not going to, you know it's going to be such a bad edge, you might as well use a sparser graph, since sparser graphs are easier to work with. Okay, so it depends upon your application. Okay? Okay, well, that should be convincing. Another thing that minimum spanning trees turn out to be good for is in clustering problems. Suppose, let's say, that we were plotting, just as an example here, let's think of two things. Let's say we were going to plot, plot people, okay? And let's say we're going to plot their wealth, okay, versus, let's say, their, okay, here I'm going to get myself in trouble. Let's say we're going to plot them by their compassion. Okay? Now, and let's just plot some points. Let's think what might happen. Okay? Historically, I don't want to sound too much trouble here. You might well end up with a picture that looks something like this. Okay? Okay? Where presumably people, you may notice somehow when people get wealthier, maybe they get less compassionate. I don't know. I'm getting myself into trouble here. Okay? But when you're looking at this chart, what do you notice about this particular data? Okay? You should notice it falls naturally into two different clusters. Okay? One common problem in data analysis is, given a set of points, you want to figure out where the natural clusters are. Okay? Again, this is maybe a silly example, but it should be clear if you want to plot, height versus weight, let's say. Okay? Or, I mean, it's just a very common thing to want to compare two things and see where the natural groupings are. Like, for example, in this case, we might want to say that there are two natural groupings. Maybe these are the Republicans and these are the Democrats, let's say. For example. Okay? How could we go and find, your input problem is you've got a bunch of points. How do you find the clusters? Okay, can someone give a sort of an algorithmic idea for taking as input a set of points and as output finding sort of reasonable clusters? Okay, this is a seemingly hard problem. Okay, and there's lots of different ways you might do it. But does anybody have any idea? Okay, well, what happens if building a minimum spanning tree? What is the minimum spanning tree of these points likely to look like?
And probably you have only one edge between the left and the right cluster.
It's going to have a lot of little cluster edges here, no doubt, something like that, and a lot of little cluster edges here, and then one big edge between them, correct? So one good way to do this, okay, is to build the minimum spanning tree, see where the large edges are, okay? If the edges are, delete any large edge, what you're going to be left with are connected components. Each connected component is likely a logically connected cluster, okay? And so one of the major clustering ideas is simply based on minimum spanning trees, okay? And this should give you an easy way to formulate that, okay? Recently I was visiting this company that wanted to, that had a printed circuit board problem. Actually, they had, as it took as input, they had a bunch of points representing where there were contacts. And they wanted to break these points into smaller clusters, okay, so that they could do the circuit analysis on each cluster by itself. And again, basically what we told them was, build a minimum spanning tree, and the clusters will sort of form naturally. Maybe this is going to be a cluster, this is going to be a cluster. Okay? Any questions about that? Finally, minimum spanning trees are easy to compute, and they tend to be useful in solving lots of other problems that are not, or approximating other problems that are not so easy to compute. The classic example is the traveling salesman problem. Suppose, let's say, that you've got a set of points, and you want to find the traveling salesman tour of these points. What was the traveling salesman back home? One thing you could do is, that's a hard problem. One thing you could do is build the minimum spanning tree on those points. Okay? The minimum spanning tree is going to use, you're going to use each edge in that tree once, and then take shortcuts. Suppose we now did a walk along this minimum spanning tree. We walk from here to here to here. Okay, I now want to walk to this point. I could walk down to here, but that would visit that point more than once, correct? So I walked 1, 2, 3, 4. I could walk back to there and get back there, but that would visit that edge twice. Why don't I then go as the crow flies? If I go as the crow flies, if this is really a geometric problem, if it satisfies a triangle inequality, the cost of getting from here to here directly from here to here. Okay? So if I do it this way, I know that I can walk to every point, and I will see no edge. I will use no more than twice the total edge length of the minimum spanning tree. Why is that? Because if I walk all the way around the minimum spanning tree, doing a depth-first search on that tree, I will walk over each edge twice, correct? There, back, back. If I take these shortcuts, it can't be making the tour any longer, okay? And further, it turns out the minimum spanning tree is always less than the traveling salesman tour. So if you believe that, okay, then by doing this tour, you're always going to be no worse than twice as bad as the optimal tour, okay, in an easy-to-compute way. Okay? So the bottom line is minimum spanning trees give us a new way to think about graph problems, and they're very useful. Any questions about any of these applications? Okay, good. So how do we find minimum spanning trees? Okay. There are two different algorithms which both work, both of which do interesting things. Is that clear? Or okay. What it's going to be is as follows, okay, with Prim's algorithm. Prim's algorithm is going to start from one vertex of the graph and grow the rest of the tree one edge at a time from that starting point. Okay? What does this mean? Let's look at an example quickly. Here we've got a graph. Zoom it in. Here's a graph. You'll notice that the edges are weighted. We start from this vertex, but tree one edge at a time, okay? Meaning that we're going to add one vertex at a time to our tree and grow it out from here. What is the cheapest way to grow out from this vertex A? Okay?
Take the edge with weight 4.
Take the edge with weight 4. That's clearly the cheapest possibility to enlarge this tree. Now we've got a tree containing A and B. What's the cheapest way to enlarge this tree further? Which edge can I take? You could go to C, or equivalently, you could go to H. Okay? They're both the same edge weight. Okay? So, but because there can be more than one minimum spanning tree, it turns out it doesn't matter. We'll arbitrarily pick one. Okay? And now we're up to here. Which is the next vertex we're going to want to add to our tree? I. Why? Because of all the vertices in our tree and all the things that are adjacent to it. We could get to here at a cost of 8. We get to here at a cost of 2, here at a cost of 7, here at a cost of 4. Darn right, we're going to take the I. What is the next vertex we'll add to the tree? Okay. What's the next vertex we'll add? Okay. Well, if we take a look at this thing, we can add F at a cost of 4. Add D. It cost us 6 to add that, 7 to add H. Cheapest thing we can do is add F. What's the next cheapest edge we can add? Okay. Which one? G. Okay. We could add G at a cost of 2 by going this way. Now notice there's more than one way we could add G. We could have added G by going from I or that, the cheapest way. Okay, there's that kind of conflict we're going to want to resolve. So we might as well pick G as being the next one. Which is the next cheapest edge we can add? Okay, well, we could add an edge of weight 6. But that would be a bad thing to do, because that's going to create a cycle in our graph, correct? We could add this edge of weight 6. But that creates a cycle. It's no longer a tree. So that's exactly the wrong thing to add. Vertex we can add. We can get here in 7. We can get here in 1. Darn right, we're going to add H. Okay, and the remaining ones, which is the next one we're going to add? D. And which is the next one we're going to add? Well, E, because I'm using the edge of weight 9. Okay, that is Prim's algorithm. We start from one vertex and keep growing in that direction. Yes?
Does it have to start at A, or start
You can start at any vertex. You pick whichever vertex you want to start.
But will each choice of vertex give you the same tree?
Okay, now the question, will each vertex give you the same tree? Now we're getting into questions of correctness. Okay? This Prim's algorithm is clearly a very simple algorithm. Okay? Okay? Clearly, it will end up with a spanning tree. Okay? Why? Because we start out, so long as there's something not in the tree, we add the lowest weight edge between something in our tree and something not in our tree. The fringe is going to be the vertices that are not in the tree yet. Okay? Once we find that one, we add it to the tree and keep looping. It should be clear that this will create a spanning tree. It should not be clear, necessarily, that it creates the minimum spanning tree. Okay, because you're right. How do we know which vertex we started with? How do we know that when they were ties that we didn't have any trouble? Okay? This is one thing we have to prove if it's right. Okay? Why is it that this algorithm is going to be correct? Okay? The basic idea, once you see it, is really very simple. Okay? Let's look at the theorem with all the verbiage. Okay? And then we'll take a look at the proof and score it, make sure we get it right. Suppose we have a connected weighted graph. Okay? And we have some set of edges, some subset of the edges in the minimum spanning tree. Okay? Let V prime be the set of vertices incident with that edges, with those edges. If there is an edge in the minimum spanning tree of minimum weight, okay, such that one edge is in that subset, one vertex is in that subset, and one edge is not in that subset, then the union of the previous edges plus this new edge is still a subset of a minimum spanning tree. This is the criteria that if we can prove this, that will prove that our algorithm is correct. Why? Because we say that if we start out with a subset of edges in the minimum spanning tree, originally we're starting out with an empty subset. Okay? So clearly we haven't gone wrong. We don't have any edges that shouldn't be there. If we always at each time add an edge that goes between a tree vertex and a non-tree vertex, okay, if this theorem is true, then we know that if it was so far a subset, adding this edge will still leave us with a subset of a minimum spanning tree. If we keep doing this, we know that we've got it. Okay? So how many people believe this criteria is enough to prove the correctness of Prim's algorithm? Okay? How many people believe? How many people do not believe? Okay? A couple people don't believe. Okay? Why is it doing? Well, what is Prim's algorithm doing? Prim's algorithm is constantly looking for the edge of minimum weight, okay, such that one edge is in the tree and one edge is not in the tree. That's exactly what it's doing, yeah.
You say is an edge of minimum weight over what?
Over all edges, with the property that one is in the tree, vertex is in the tree, and one is not in the tree. So what are we going to do? We're going to at each round scan through all the edges, find the one which the minimum of all the edges. We're going to look at which edge has 1 foot in and 1 foot out, okay, and pick the one that is minimized. Okay. The claim here is that if we had before a subset of edges of a minimum spanning tree, we add this thing, we still have a subset of edges of a minimum spanning tree. There are lots of different minimum spanning trees, but we know that we haven't gone wrong. There's still going to be one that's going to be right. Okay? And so long as we have that, we know we will end up correctly with a minimum spanning tree. Okay? What is the argument? Okay? Let's now consider this edge that we added. Okay? There's two possibilities when we consider this new edge. That is the cheapest edge with 1 foot in and 1 foot out. Either this edge is in the minimum spanning tree, or it is not in the minimum spanning tree. If it is in the minimum spanning tree, then the theorem's true. We had before a subset of edges in a minimum spanning tree. If I add the next edge that I add happens to also be in the minimum spanning tree, by definition, I haven't done anything wrong. It's still a subset of a minimum spanning tree. So that's easy. That's true by definition. What I'd like to prove to you is that it can't be anything else. Suppose that instead I have a subset of edges so far that is in a minimum spanning tree, and I add a minimum weight edge with 1 foot in and 1 foot out that is not, okay, in the minimum spanning tree. What do we now know? Okay, if this edge is of minimum weight, okay, let's just think about what could actually happen. Okay, we've been growing a tree. The claim is that now, at some point, suddenly, this edge of minimum weight is not going to be in a minimum spanning tree. Okay? Two possibilities exist. This edge, okay, now consider the new minimum, no, now consider the new edge of minimum weight associated with that. Suppose that isn't in a minimum spanning tree. Okay? Let's now go back and think what happens when we add other edges, the rest of the minimum spanning tree. Okay? Okay, that. The blue is what we originally had. The orange here is a vertex that we didn't, that is the edge that we wanted to add, but they're claiming we make a mistake. The black is the rest of the minimum spanning tree, okay, that is formed with this blue edge. Correct? By definition, these blue edges were part of a minimum spanning tree. If we went wrong here, that meant that this orange edge, which we wanted to add, did not belong in the minimum spanning tree. And in fact, the black was the rest of the minimum spanning tree. Okay? What do we know about this edge? Okay? We know that this edge has to be of lowest weight of any other edge, okay, that we could have picked at this moment that was adjacent with 1 foot in and 1 foot out. Correct? That's why we chose it, because this was the cheapest edge that touched the blue. Okay? If we add that edge now to the minimum spanning tree, what will we now have? Will we still have a minimum spanning tree? No, we're going to have a cycle. Correct? It was a minimum spanning tree. If you add any edge to the spanning tree, you're going to create a cycle. Correct? How many people believe that? How many people do not believe it? Okay, everybody believes. What do we know about the weight of this edge here? This edge had the property that, okay, it was picked afterwards, okay, it has 1 foot in and 1 foot out. What do we know about the weight of this edge relative to the weight of that edge?
Cannot be shorter.
It cannot be shorter, okay, and if it's bigger, okay, does everybody believe that it can't be shorter? Because if it was shorter, we would have picked it. That was the criteria by which we picked this edge. Suppose this edge is now longer. What happens if, let's say this was of weight 10 and this was of weight 11? What happens if I now add this edge to the tree and delete this one? Okay?
You have a smaller minimum spanning tree?
I have a tree, a set of edges that clearly has smaller weight, okay, because I deleted somebody of 11 pounds and replaced them with somebody of 10 pounds. Clearly it's lighter. Is it still a spanning tree? Well, if I have a cycle, I could snip out any edge and it's still going to be connected, correct? So it's still got to be a spanning tree, and it's got to be lighter. Okay? If it's got to be a spanning tree and it's got to be lighter, I could not have had a minimum spanning tree by taking the heavier guy instead of the light guy. Okay? So therefore, my algorithm was correct. Okay? Working in the greedy way always did the job. Question?
You didn't explain the case that the 11 pound actually was also 10 pound.
Suppose that these things were 11 point and 10 point. You're saying, what if this thing was also 10?
Also 10, yeah.
Okay? What would happen if I deleted this one and replaced it with that one? I get an alternate spanning tree, which has exactly the same minimum weight. So if you're telling me that this was a minimum spanning tree, and that I did something irrevocably wrong by picking this edge, no, I didn't do anything irrevocably wrong. Because if, in fact, this edge was the same weight as that one, I could have picked this one and not picked that one. I would have ended up with a spanning tree of exactly the same weight. So that is not true. Okay? I could not go wrong by always picking the smallest adjacent edge. Question?
But typically, when you accept both and defer your decision to the further up in that loop.
So one claim is, could I accept both of them and not create and delay the decision later on? What would presumably happen is that I would, if I have a bunch of edges of the same weight, okay, I would pick them in, I could pick them, I mean, before I go and add any edge of weight 15, I'm going to add that other edge of weight 10. I can't by default add all the edges of weight 10 at one point, because I could end up with a situation where I had two edges of the same weight going to the same place. So adding each edge at one edge at a time prevents me from creating cycles. Okay? But it doesn't matter which edge I add. Okay? Think about it. If you have an unweighted graph, does it matter which spanning tree you pick? How many edges will every spanning tree of a graph have if you have n vertices? N minus 1. It doesn't matter if they're all the same weight which one you pick. Okay? Ties don't cause you any trouble. And they don't cause you any trouble here either. Okay? Any questions about how many people believe the proof? How many people do not believe the proof? Okay, everybody believes. Okay? The argument is based on adding that edge back and looking at what happened. Okay? Once you see that, everything becomes clear. Okay? Prim's algorithm is correct. Any questions? Okay?
What is the
Yeah.
asymptotic running time?
So now the question is, if we believe Prim's algorithm is correct, a second question, okay, is now how fast is Prim's algorithm? Okay? And this now depends upon exactly how we're doing. So first of all, are there any questions? Is there anybody who does not believe that Prim's algorithm is correct? Okay, that constantly starting from the tree, picking the next best edge, the cheapest edge that will grow our tree by 1 node. That's a winning strategy. Now the question is, how do we go and implement that in a computer? Okay, and what is the fastest way that we can do that? The pseudocode for Prim's algorithm looks like this. We select an arbitrary vertex to start. How much time is, given a graph, let's say in adjacency list form or adjacency matrix form, how much time does it take to select an arbitrary vertex? Constant time. Look, vertex 1, boom. Okay, we selected that. That's easy. While there are non-tree vertices, select the minimum weight edge between the tree and the fringe. Okay, and then add that to the tree. How many times is this loop, while loop, going to go around? N minus 1 times, or order n. Again, okay? Suppose, let's say, we label each vertex. Once we add it to the tree, we mark it as being in the tree. Okay? And before that, we just leave it as unmarked. Okay? So one thing we could do is have an adjacency list structure, where for each vertex, v1, v2, we have a flag associated with it. Is it in the tree or is it not in the tree? Initially, we initialize them all to false. How much time would it take to set the flag on the ith vertex to say it's in the tree? Constant time. So in constant time, we can tell whether a vertex is in the tree or not. Okay? My claim is that by now looping through all the edges, okay, we could take each edge and say, is one vertex in the tree and one vertex not in the tree? If not, we don't care. If one vertex is in the tree, one vertex is not, is this cheaper than any edge we've seen so far? If so, keep it around till we do better. We could do the selection, I claim, in linear time and time linear in the number of edges. Order m edges. Correct? So the total time for this could be done trivially in order n plus m time. N iterations, each iteration takes order m time. N times m time. Okay? How many people believe that? Okay? How many people do not believe that? Okay? Everybody, nobody confesses to not believing it. It's important to see where this comes up because we're going to improve it. Okay? But the trivial analysis is order nm. Okay? What is the bottleneck in this algorithm? What is the thing that if we look at this, we might hope to do better? Do we hope to add less than all the vertices to the spanning tree? No, I don't think we're going to be able to prove that side. What is the thing we can hope to improve? Okay?
We only look at those edges on the what we call fringe.
Right. Only look at the edges on the fringe. Okay? But actually, looking at only the edges on the fringe is not really good enough. Okay? Suppose we have a tree where we've got, here's our tree so far. We've got, let's say, n over 2 vertices here. There's n over 2 vertices that are not in the fringe. If we just look at, we could have where there's an edge from every one of these to every one of those. We don't want at each point just to look at the edges that are half in the fringe and half not in the fringe, because there could be a lot of them.
Yeah, so we keep a kind of priority.
What we want to do is to keep track of which is the best edge to each vertex that's not in the fringe. Okay? If you think about it, we don't at each point want to go through all possible ways of linking it. What we'd like to know is what is the best way we've seen so far to link that vertex in. Okay? So instead our picture would be, here's the stuff that's in the tree, here's the stuff that's not in the tree yet. For each thing that's not in the tree yet, we'd like to know what's the cheapest way of potentially getting it into the tree. Okay? And the important point to see here is that while this could be order m, how many possible edges can there be where we only consider for each vertex here the cheapest way of getting it into the tree? Okay? There's going to be exactly one edge coming out of each non-tree vertex, correct? How many edges can there be that are colored orange? Okay, if you have n vertices and m edges, how many orange edges could there be? N instead of m. So our idea is going to be keep track of the cheapest way to do it. Okay? We need to be able to identify which the fringe vertices are quickly. Okay? We can do that by using a data structures in the proper way. Okay? How do we do it? For each vertex, we're going to keep a couple of different things. Again, there's lots of different ways to do it. This is one way I stole from a book. The textbook here probably does it a little differently, but it's all equivalent. For each vertex, okay, we're going to maintain its status. Is it in the tree? Is it a fringe vertex, or have we not discovered it yet? Okay? If we haven't discovered it all, it's unseen. We're going to keep for every vertex what are the list of all the vertices we can reach from that vertex. That's the adjacency list. For each vertex, we're going to keep track of its parent. Okay? What is the vertex we've discovered that has the cheapest wedge weight to this one? Okay? Fringe weight. What is the cheapest edge linking this vertex into it? Okay? And a fringe link pointer to the rest of the fringe. Okay? This I don't want to go into so much. But what's the point? If for each vertex that's not in the tree, we know what's the cheapest edge linking it to the tree, what are we going to do? Our innermost loop is simply going to go through and loop through all the vertices. There's n of them, and say, which of them are you in the fringe, and if so, what's your fringe weight? The cheapest one is what we add. Okay? Any questions? Question? Between fringe and unseen. The difference, if you think about it, how's the graph going to evolve? We start out from one vertex, and we look at, slowly we're growing a tree. The underlying graph is going to have several different classes of vertices. There's going to be some vertices which are not connected by one edge to the tree. There's other edges, vertices that are within a distance of one of the tree. The vertices that are within one edge of the tree is the fringe. Since we're starting out here and growing it, there's other vertices that we've never considered. Because we're starting from our tree and walking out. We haven't gotten far enough yet. So the unseen vertices are the undiscovered ones. Okay? That's why we have that possibility. Any questions? Pseudocode for the algorithm, I would look at it like this when you look at the proper data structures. For any vertex, okay, what are we going to be doing? We initialize it properly. Okay? What's the idea? It's maybe from yet another book. Okay? But what are we basically going to do? We're going to have a loop that's going to go around. While we haven't added all vertices to our tree, loop, okay? First thing that we're going to do is we've added, for each fringe vertex, we've now, in each edge of the vertex, we're going to be adding a new vertex x. Okay? For each fringe vertex that's adjacent to the new vertex we just added to the tree, if this new vertex we added to the tree provides a cheaper way to do it, to get access to it, then update that fringe cost. If before the cheapest way to get the vertex y was 10, and the new vertex we added, x, was able to get the y at a cost of 5, now we're going to change the potential parent of y from what it was to x. Does that make sense? Okay. Is there anyone that doesn't make sense to? Okay. Don't be afraid to say so. Okay. So here we're going to replace candidate edges. The other possibility is that now there's going to be some vertex that we've never seen before. Okay. If there's some vertex we've never seen before that's adjacent to the new thing we added, then the cheapest way to get to that new vertex is going to be through the thing we just added. So make these new guys fringes and make this edge be the candidate cost. Now we've updated it, updated our data structures. Okay? How do we decide what the next edge is? Well, loop through for every vertex in the fringe, keep track of what was the cheapest edge. Okay, go through all the vertices in the fringe and find out what was the cheapest edge we know of between the fringe and the tree. That is going to be the fringe vertex, and that's going to be the edge we add. And then the thing cycles again. So what's the time this thing takes? How much time will it take to cycle through? We go back to the global picture here. How much time does it take to cycle through for every fringe vertex, all its adjacencies? Well, how many vertices can a fringe vertex be adjacent to? At most every other vertex in the graph. So the new vertex can be adjacent to at most n things to check. The new vertex can be adjacent to at most n things to check. Okay? And finally, since we now consider one edge to every undiscovered vertex, since we have those edges stored in our data structure, we scan through that, one edge per fringe vertex, that takes order n time. The total thing is n loops of 3 times order n time. Okay? Order n squared time. Okay? Any questions? Okay? Let's just take another look at that. Okay? Again, the bottom line here, when you look at the notes, we're going to be adding each vertex to the tree, takes linear time. We're going to do it n times. Total time is n squared if we use the right data structures. Okay, any questions? Okay? It should be easy to see that prims can be implemented in order nm time without the data structure. Make sure you understand that first. Then go back and see how we're solving the problem that was the bottleneck in linear time, linear in the number of vertices. If so, then this should make sense. Any questions? Question?
Do we always have to use n squared? I mean, if you, for example, would not scan through all the fringe edges, but have the fringe edges in a binary tree or in a heap or so, then you can just pick the next button.
So one idea that might be to speed this thing up is going to be, suppose since at each point, if we take a look at the main loop here, okay? The point is that really what we need to do here is go through all the vertices that are in the fringe. That's really sort of somehow what we're doing. Okay? So, I mean, in some sense, each one of these little loops, for each fringe vertex adjacent to it, in the worst case, we could have a linear number of fringe vertices. So you don't save anything in the worst case. Okay? In specific cases, it might pay as an optimization to improve the average case time. That might not be a bad idea. Okay? But in the worst case, you could have a linear number of fringe vertices. Okay?
So this would be something in a complete graph. Would be worst case.
Let's say in a complete graph. Okay? A complete graph with, let's say, weights where, let's say, every edge was of weight 1. I claim that would take n squared according to this. Okay? Any questions? Okay? So again, I agree that's a good heuristic, but a good way to speed it up. But on the other hand, in the worst case, it doesn't help us. Okay? Any questions? Okay. There's another algorithm for minimum spanning trees that also turns out to be useful to think about. Okay? This algorithm is called Kruskal's algorithm. And it's motivated by the fact that what was noted here, although Prim's algorithm took order n squared time, okay, that's optimal in the case where you've got a dense graph. Because if you have a complete graph, you have to look at every edge. It seems reasonable to say you have to look at every edge to find the minimum spanning tree. This takes order n squared time, independent of how many edges there are. So on a dense graph, Prim's algorithm is perfect. Okay, can't hope to beat it. Okay, maybe by a constant factor, but no reason to talk about it anymore. The potential win is, what if we have a sparse graph? Okay, and most graphs in the world that are interesting tend to be sparse, or large graphs, simply because it becomes impossible. A lot of times you're interested in having graphs on a lot of vertices, and just because the number of edges grows quadratically in that, usually people are limited to sparse graphs for lots of different applications. Can we find a faster algorithm in the worst case for sparse graphs and minimum spanning trees? Okay? The answer is yes, we can, and it's called Kruskal's algorithm. And Kruskal's algorithm is a different version of the greedy algorithm. If you think about it, if the greedy algorithm says that at each step, we're always going to pick the thing that looks best to us now. If we could get away with it one way, okay, namely before we started from one tree and grew something, okay, maybe we could get away with it in another way. Kruskal's algorithm says, start with all the vertices, okay, and no edges. Repeatedly add the edge, okay, of smallest weight of all the edges in the graph, which does not create a cycle. Okay, so what is the example here? Here is our graph. Okay, same graph as before. What was the edge of cheapest weight? Well, if you scan through this thing, there's an edge of weight 1. Okay, and nothing else of edge weight 1. Kruskal's algorithm says pick the cheapest edge. What is the next cheapest edge in the graph? Okay? 2 twos. Without which one should we pick? Doesn't matter. Okay? So here's an edge of weight 2. Let's pick that as our next cheapest edge. Okay? Which is the next cheapest edge in the graph? Another 2. Pick that one up. What is the next cheapest edge in the graph? There's no 3, so a 4. We've got a choice of that 4 and a choice of this 4. Okay? We happen to add that one. What's the next cheapest edge in the graph? Next 4. Select that. We've got that. What's the next cheapest edge in the graph? 6, but. Okay? What happens if we add 6? Get a cycle. Can we have a cycle in a spanning tree? No. So that edge has to get punted. Okay? What is the next smallest edge that we can add? Okay? We can add the edge of weight 7. I think this is right. Okay? Let's go back to here. Actually, I think this is right. Okay? What's the next edge we would add? Okay? There's another 7 where? Okay? And that's fine. We can add that one. No, we can't. Why not? Because is that going to create a cycle? Yes, it will. Okay? So now we're back to here. What's the next edge we can add? An edge of weight 8. Is that edge of weight 8 okay?
Wait, which one? BC?
We could add either this one or that one. Does it matter? Well, why don't we add this one? It doesn't matter. What's the next edge that we can add? There's another edge of 8. Can we add this edge now? No, because now we got a cycle. Edge of next one's of edge 9. This does not create a cycle, so let's go for it. Okay? and now we have every vertex in there. We have no cycles. This is a spanning tree. Okay, any questions about the strategy here? It should be clear that this is a spanning tree. Okay? We had a graph. We have found a spanning tree. Okay? It has no cycles. Why is this the minimum spanning tree? That's the issue that has to be resolved. Okay? The basic reason is the proof is going to be very similar to the proof of the other one. Okay? Suppose it didn't work. Okay? How would it say if Kruskal's algorithm didn't work? What would we say had to have happened? We would have to have come up with a situation where we have added a bunch of edges to our spanning tree, and suddenly we go wrong. Expensive. We're adding these edges confidently, and suddenly we make a mistake. Suddenly that there is a moment in time where what we have now by adding this edge will not create a minimum spanning tree. That couldn't have happened by adding an edge to create a cycle, because we would never have added that edge to the tree. Every edge we add is not creating a cycle. So suppose instead we got to a situation where we add an edge. Let's say I happen to add this edge, okay, and let's say I happen to add this edge, and suddenly God says you made a mistake, okay? Everything you had so far could have been made into a minimum spanning tree, but adding this edge you couldn't. Okay? Well, what do we know? Okay? In that case, okay, there would have been, if we take this edge out, there would have been a way to complete the thing into a spanning tree. Okay? And when we complete that thing to a spanning tree, and now add this edge back into it, okay, if we had a spanning tree, and this extra edge was not in it, adding that edge will do what? Create a cycle. What do we know about this last edge in that cycle? Okay, the first edge that if we take this edge in the graph, there's going to be some edge in that cycle that wasn't there when we were considering this edge. Why? Why do we know that there had to be some edge that wasn't? If this was the edge we were going to add by Kruskal, why do we know that there had to be edge added later? Because Kruskal wouldn't have added it if it was going to create a cycle. So we know there was some edge that we didn't consider yet. What do we know about the edges we didn't consider yet? They're all of weight greater than or equal to this edge. So if we take the largest edge on this cycle and delete it and replace it with this, we still have a minimum spanning tree, and its wedge has to be, its cost has to be less. Therefore, Kruskal's algorithm has to give you a minimum spanning tree. Okay? And again, we can break ties arbitrarily. Any questions about that? Okay, how many people follow the proof? A lot of people? Okay, good. Okay, how many people don't follow the proof? Okay, very good. That said, Kruskal's algorithm is correct. How much time does it take to find minimum spanning trees by Kruskal's algorithm? Okay? Again, do the simple version first. How much time does it take to sort m edges? Okay? You have m edges, m edges, each edge has a weight associated with it. How much time does it take to sort them by weight? M log n. You sort by, use any sorting algorithm that's good. Okay? Now what we need to do is consider these edges from small to large. You know, somehow we're going like the edge weight from 1, 1, 3, 5, 7, 9, something like that. Okay? For each edge, what do we need to do as we consider it? We're going to add this edge unless it creates a cycle with the tree we have so far. Correct? How can we test whether or not adding this edge is going to create a cycle? Okay? Depth first search. Why? We now have a graph that we're building. Slowly we're adding edges to this graph. This graph is the tree that we're building. The query we need to be able to solve is, add an extra edge. Does it create a cycle? That one does not. This one does. How much time would it take to actually find this thing in a trivial implementation? How many edges are there in the graph that we're building of the tree? Okay? How many edges can there be in this tree that we're building? Yeah?
No more than n.
No more than n. This is a subset of the spanning tree, and the spanning tree has n edges. Okay? How much time will it take for a graph on n vertices and n edges to test whether it has a cycle? Okay? If you do a depth first search, that takes time order n plus m. What's m? M is n. N plus n is n. Okay? It takes order n time to test if it's a cycle. Okay? So the trivial implementation of this would be, for each of the m edges, do an order n operation. N times m time. Okay? Question?
Well, if we kept track of the vertices that had been included up to that point, couldn't we do it in constant time?
The question is, if we kept track of the vertices that we'd already had sort of touched edges to, could we do that in constant time? Well, it depends upon how many vertices we've already added. Okay? We're starting out now with an empty graph. Okay? We're starting out with a bunch of vertices. Okay? Initially, if I add one edge to a graph, you're right, I probably should be able to tell whether or not whether or not I have added, whether I'm going to create any. The time it takes is proportional to the number of edges I already have. I'll tell you, the time it takes to do the cycle testing is going to be proportional to how many edges I have in my tree. Correct? No?
I mean, what you're going to create is some kind of a forest of trees, right?
Forest of trees, right?
So give a number for every tree.
Okay.
And so every vertex has a pointer to
Okay.
saying what number it has.
Now you propose a cleverer scheme for this. Okay? That scheme will do the job. Okay? But let's first thing is make sure everybody agrees. If we want to test the cycles, this is the way to do it. This is the simple way to do it. Okay? You're cleverer. Okay? And you figured out a faster way. Okay? This is the first thing that I would do. Okay? And this gives me an n times m algorithm. Is there anybody who's confused by the n times m algorithm? No. If we want to speed it up, where is the money? Okay? Sorting it in m log m time, well, we're only looking for something that's going to do well on sparse graphs. Okay? For dense graphs, this is going to be what? What's this going to be for a complete graph? N squared log n squared. What's log n squared? 2 log n. This would be order n squared log n. So for dense graphs, we lose already here. But for sparse graphs, we win big. N log n is better than n squared. The thing we need to do here is to find a faster way to do this test. Okay, to do this cycle test. Okay? And the idea that was noticed here, okay, is that if we could in some sense label each component, each tree in the forest we're building up with a name. If each tree in the forest has a name, the edges that will not create cycles will be exactly the edges that go between two different trees. Correct? Here we've got a tree. We'll give this one a name. Maybe we'll call this one birch. Okay, we have this tree. Maybe we'll call this one oak. There you go. Okay? If we have an edge between birch and birch, we're in trouble. Can't use it. Edge between birch and oak, we can use it. So my claim is, okay, if we could quickly determine what's the name of the tree that a vertex is in, we could do this cycle testing quickly. Okay? The cycle testing problem reduces to the problem of testing what the name of a component is. Okay? So, what's the idea of the algorithm? Put the edges in a heap, namely, which is equivalent of, so we can retrieve the smallest and the smallest remaining ones. This is the same thing as sorting them, since we're not going to create any new edges. While we don't have enough edges to make a tree, get the next smallest edge. If that edge spans two different trees in the forest, add it to the minimum spanning tree, okay? And then set the name of these two trees to the same. Because remember, if we now have a graph between the oak and the birch, okay, now they're no longer separate trees. Okay, their identities are now the same. Okay? So what are the operations we need to do this? We need to be able to maintain a set of trees, the names of vertices in trees. Okay? And there's two things we have to do. What are the two operations we want to be able to do to our trees? Okay? We want to be able to ask a vertex, what is your name? And you want to be able to take two trees and say, now you're the same name. Okay? If we can do those operations, my claim is we can solve minimum spanning tree fast. Okay? Any questions about that? Okay? How many people see that if we could do the name operation, namely, find out what's the name of a tree, of the tree that a vertex is in, and what's the name, and take two trees and merge them together. If we could do both of these things in log n time, my claim is we could find minimum spanning trees in m log m time. Why? Because for each operation, for each edge we pull out, we're going to do a what's your name, what's your name, are they the same? If so, merge. If each of those operations, your name and merge could happen in log time, the total time is m log m. Okay? Any questions? How many people believe? How many people do not believe? Okay? You don't believe, or you're suspicious?
What is this if we can test components in O of log n?
If we could test whether or not if we can implement this component query, which basically what is the name of the tree, the subtree, if we can implement that operation in log n time, why? Why do we need log n? You say you can do it in constant time?
Why can't every vertex have a pointer to its name?
Well, why can't every vertex have a pointer to its name? Okay? Suppose we have a tree here. Okay? Every vertex, this is now the oak tree, right? Maybe oaks have nice branches like that. Okay? And we've got n over 2 vertices here. And here we've got the birch tree. And this has n over 2 vertices. Maybe each now knows what the name of what its name is. I'm an oak, I'm an oak, I'm an oak, I'm an oak, I'm an oak. Okay? I'm a birch, I'm a birch, I'm a birch, I'm a birch, I'm a birch.
Well,
how much time will it take when we decide to turn our oak into a birch? What do we have to do? Okay, if every vertex explicitly has its name,
no, it's just a pointer to the name. And then the field with the name.
every vertex has a pointer to its name.
Right.
So now you're going to tell me that these guys are now pointing to its name.
Right. And then you just change that name field from oak to birch.
Okay, so this was now an oak. This is oak. This is now birch. And everybody's pointing to this thing.
So leave all the pointers as they are. You just make the content of the field to be the same.
And so now what am I going to do now when I merge these two?
Take one of them and replace the name. Say birch merge is not going to be old also.
Okay? So now you're claiming to tell whether or not two things are
And the same thing.
do the merge in constant time per operation. Now, why doesn't that work?
Because when you built the tree, you built from the bottom up, so each one had a tail. So you still had to go and add all the tails.
No,
Okay, because look what's happening now.
but that doesn't matter.
So you're not claiming that every vertex will have associated with it a flag field. Okay? Now I'm going to, originally each vertex starts by itself, correct? Each vertex has its name. I'm a little oak. I'm a little birch. Okay? I'm a little spruce. Okay? Now you're telling me you're doing a merge operation. Every time you merge that thing, you've got to change both of these fields. Okay? If every vertex has a field name associated with it, you're still going to all these things point to the same place. The only way they point to the same place is if you had manipulated all of those pointers. So it can't be done that trivially. Okay? It can't be done in constant time. Okay? Next class we'll see how it can be done in log time. Okay? Good questions. Any questions? Daily problem. Next class I'll do the daily problem for this class. Since you had an do next class. Okay. Thank you.